Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the mystery of Three-Eye Atlas, a visitor that may have travelled between the stars to reach us. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who have already joined, a long thank you. The object arrives like a whisper in the cosmic dark. Detected first as a smudge against the star field by the Catalina Sky Survey on a September morning, when Earth's atmosphere trembles with autumn's first breath. Three-Eye Atlas measures perhaps 400 meters across, tumbling through space beyond Jupiter's orbit at 26 kilometers per second, faster than any human-made object, yet still carrying the unhurried patience of deep space in its movement. Its trajectory curves in ways that suggest it has never felt our sun's gravitational embrace before this moment, never known the gentle tug of our star's influence across the vast reaches of the solar system's outer darkness. The designation 3I marks it as only the third confirmed interstellar object to visit our solar system, a wanderer from the spaces between stars where matter grows thin and cold, where the nearest stellar companions shine as distant points of light separated by gulfs of emptiness that would take human spacecraft millennia to cross. Before Three-Eye Atlas, astronomers had catalogued only Oumuamua in 2017 and Tusai-Borisov in 2019, each carrying their own mysteries like cosmic messages written in languages we struggle to decipher. Astronomers track its motion with the patience of deep time, recording positions across months of observation as Earth spins through its seasons and the object continues its ancient journey. The numbers accumulate like sediment in a river delta, each measurement adding weight to an impossible conclusion that grows more certain with every passing night of telescope observation. This object follows a hyperbolic orbit, its path bending just enough around our Sun to steal momentum before continuing toward the constellation Lynx, where it will fade back into the interstellar medium from which it emerged. Only comets born in the Oort cloud typically move this way, following trajectories that speak of origins in our solar system's most distant reaches, where the sun's light grows so faint that temperatures hover just a few degrees above the absolute zero of empty space. Yet Three-Eye Atlas shows no signs of that distant nursery's icy signature. No crystalline structures formed in the primordial collapse that birthed our solar system 4.5 billion years ago. Instead, it carries the chemical fingerprints of elsewhere isotope ratios that suggest formation around a different star, in stellar nurseries we have never seen. The visitor maintains its silence as it approaches perihelion, that closest point to our star where comets traditionally announce themselves with brilliant tales of sublimating ice, transforming from dark wanderers into glowing beacons visible to the naked eye. Instead, Three-Eye Atlas offers only the faintest whisper of reflected sunlight, absorbing solar radiation with an efficiency that speaks of surface compositions, unlike anything familiar from our own celestial neighbourhood. Telescopes strain to glimpse its surface features, catching hints of something darker than charcoal, darker than the carbon-rich meteorites that occasionally grace our museums with fragments of the early solar system. The object's albedo measures just 4% darker than fresh asphalt, darker than the carbonaceous asteroids that drift in our system's shadows, like ancient remnants of planetary formation. This darkness suggests surface materials that have been processed by cosmic radiation for eons, their original compositions altered by the patient bombardment of high-energy particles that stream through interstellar space. Only the most refractory materials survive such exposure unchanged, creating surfaces that absorb light with the hungry efficiency of cosmic sponges. Time moves differently for interstellar travellers, flowing at scales that dwarf human comprehension and stretch beyond the boundaries of recorded history. This object has perhaps wandered for millions of years through their galaxy's spiral arms, threading between stellar systems in the cold dark where temperatures hover mere degrees above absolute zero, and matter exists in states of near-perfect crystalline stillness. Its surface bears no atmosphere to speak of, no protective cocoon of gas that might preserve secrets from its origin, or shield delicate structures from the erosive effects of cosmic rays. Instead, it presents itself as raw matter sculpted by the universe's most patient forces, solar wind from distant stars. The gentle pressure of starlight accumulated over geological timescales, and the constant rain of cosmic particles that permeate the galaxy's disk. These influences work like cosmic weathering, gradually modifying surface chemistry and removing volatiles that might otherwise provide clues about the object's birthplace. Only the most stable materials remain, creating a kind of interstellar desert where traces of the original composition hide beneath layers of space-weathered regolith. The mystery deepens with each passing observation, each night of telescope time revealing new contradictions that challenge existing models of how objects form and evolve in the spaces between stars. Most interstellar objects should arrive with velocities reflecting their galactic motion, carrying the kinetic energy of their journey through the local standard of rest, that reference frame, in which our solar system moves through the galaxy's gravitational field. Yet 3i Atlas moves too slowly for its presumed age, as if it has been travelling for far longer than the mathematics of galactic dynamics would suggest. Spectroscopic analysis reveals surface materials that reflect light in patterns inconsistent with known mineral compositions, creating absorption lines that appear in wavelengths where familiar substances should remain transparent. The object's thermal signature likewise defies easy interpretation, radiating heat in ways that suggest internal structure more complex than simple rocky or icy compositions would produce. These anomalies accumulate like evidence in a cosmic detective story, each observation adding another piece to a puzzle that refuses to resolve into familiar patterns. Only took a few million years to cross between stars. Yet somehow 3i Atlas seems older, more patient, carrying the weight of journeys that predate our solar system's formation and the slow accretion of planets from the primordial disk that once surrounded our young sun. The universe, it seems, has been keeping its own schedule all along, moving objects between stellar systems according to rhythms that operate on timescales beyond human intuition. In the vast patience of cosmic time, even the journey between stars becomes just another moment in the endless dance of matter through space, carrying messages written in languages of physics we're only beginning to learn to read. The silence of 3i Atlas speaks louder than any comet's brilliant tale, suggesting origins in stellar systems where the laws of chemistry and physics might assemble matter according to different rules than those that governed our own solar nebula's collapse into the familiar architecture of rocky inner planets and gas-giant outer worlds. The spectroscope reveals its secrets slowly, like ancient writing emerging from palimpsest under patient examination. When astronomers split 3i Atlas's faint reflected light into its component wavelengths, they discover absorption lines that speak of carbon monoxide where water ice should dominate. This molecular signature puzzles researchers who have spent decades studying cometary composition, familiar with the predictable chemistry of objects born in our solar system's outer reaches, where water freezes into the crystalline matrices that define most icy bodies. Carbon monoxide requires different conditions to remain stable on an object's surface temperature so low that even this simple molecule, barely more complex than the fundamental building blocks of stellar atmospheres, can condense into solid form. In our solar system, such conditions exist only in the most distant regions of the Kuiper belt and Oort cloud, where the sun's warmth becomes so attenuated that exotic ices can survive for billions of years without sublimating into space. Yet 3 Atlas carries this molecular fossil from somewhere else entirely, preserved through its interstellar journey like a chemical memory of alien stellar environments. The infrared signatures deepen the mystery with each observation. While most comets display the telltale spectral fingerprints of water, methane, and ammonia, the trinity of volatiles that dominate icy bodies throughout our solar system, 3i Atlas presents a chemical composition that speaks of formation under different stellar conditions. The ratios between carbon and oxygen isotopes suggest nucleosynthesis in stars with masses and metallicities, unlike our Sun. Stellar furnaces that forged elements according to different nuclear recipes over the course of their billion-year lifespans. Carbon monoxide's presence poses particular challenges for models of natural object formation and evolution. This molecule forms readily in the reducing environments of stellar atmospheres and interstellar clouds, where carbon and oxygen atoms find each other in the cold darkness between stars. Yet its survival on the surface of a wandering object requires conditions that should not persist during the violent processes that typically create asteroids and comets, the gravitational collapses, impact events, and thermal processing that shape most small bodies in planetary systems. The spectral analysis continues across multiple wavelengths, each observation adding layers to the chemical portrait of an object that refuses to fit comfortable categories. Near-infrared observations reveal absorption features consistent with organic compounds more complex than simple carbon monoxide, suggesting surface materials that have undergone processing by cosmic radiation over timeframes measured in millions of years. These organics form slowly through the patient bombardment of simpler molecules by high-energy particles, creating increasingly complex carbon chains that polymerize like cosmic plastics in the vacuum of interstellar space. Photometry measurements track the object's brightness variations as it tumbles through space, its irregular shape causing predictable changes in reflected light as different surfaces rotate into view of Earth-based telescopes. These light curves reveal rotation periods that span several hours, consistent with an object that has not been tidally locked by close gravitational encounters or shaped by the rapid rotation that characterizes many asteroids formed through catastrophic collisions. Instead, 3I Atlas spins with the measured cadence of something that has maintained its angular momentum through the isolation of interstellar space. The chemical composition challenges existing models of how volatile materials survive in the harsh environment between stars, where temperatures drop to just a few degrees above absolute zero and the density of matter becomes so low that individual atoms may travel for years without encountering their neighbours. In such conditions, most molecules should freeze out onto dust grains or dissociate under the influence of cosmic radiation, leaving only the most refractory materials to survive interstellar journeys intact. Yet 3I Atlas appears to have preserved a complex inventory of carbon-bearing compounds across its millions of years of wandering through the galaxy's spiral arms. This preservation suggests either formation in environments with unusual chemical conditions or protection mechanisms that shield surface materials from the erosive effects of cosmic weathering. The object's dark surface may itself provide such protection, absorbing ultraviolet radiation that might otherwise break molecular bonds and drive away volatile components. Radio observations add another dimension to the chemical analysis, searching for emissions from excited molecules in any thin atmosphere that might surround the object. These sensitive measurements detect only silence, where other comets would broadcast their molecular signatures across the electromagnetic spectrum, confirming that 3I Atlas maintains its chemical inventory in solid form, rather than releasing vapours that might provide more direct insights into its composition and structure. The isotopic ratios present the most compelling evidence for truly alien origins, showing distributions of heavy elements that reflect nucleosynthesis in stellar environments significantly different from those that created our solar system's material inventory. The elevated abundance of certain rare isotopes suggests formation in the ejecta of supernovae or the stellar winds of massive stars nearing the end of their nuclear burning phases, cosmic events that occur with different frequencies in various regions of the galaxy. Only took 4.5 billion years for our own solar system to develop its characteristic chemical fingerprints. Yet somewhere else in the galaxy, different stellar nurseries were forging matter according to different nuclear recipes, creating the exotic isotope ratios now preserved in 3I Atlas's ancient surface materials. The universe, it seems, has been conducting chemistry experiments on scales that dwarf terrestrial laboratories, mixing elements in proportions that reflect the diverse stellar populations that have enriched the galaxy's interstellar medium over its 10 billion year history. The patience required for such chemical archaeology stretches human comprehension, demanding instruments sensitive enough to detect molecular signatures in objects darker than coal and more distant than Jupiter, travelling at speeds that make detailed observation a race against time as the visitor fades back toward interstellar space. Each photon carries information across millions of kilometres of vacuum, preserving in its wavelength the quantum mechanical signatures of atomic transitions that occurred when molecules absorbed and re-emitted starlight on the surface of an alien world, now wandering through our solar system like a cosmic messenger carrying news from stellar systems we may never visit. The carbon monoxide continues its silent testimony to conditions in distant stellar nurseries, speaking of temperatures and pressures that assembled matter into forms unknown in our local cosmic neighbourhood, where the familiar chemistry of water ice and rocky silicates has dominated planetary formation since the solar nebula's initial collapse into the architecture we now call home. The geometry of 3I Atlas defies the patient symmetries that govern most celestial bodies, stretching into proportions that violate the fundamental principles of gravitational collapse and accretionary formation. Radar observations from the Arecibo Observatory, during its final months of operation before the Great Dish collapsed into its own geometric impossibility, revealed an aspect ratio of at least 6:1, an elongation so extreme that it challenges every model of how rocky objects achieve structural stability in the vacuum of space. Natural processes tend towards spherical symmetry with the inexorable patience of physical law. Gravity pulls matter inward with equal force from all directions, creating the rounded forms we observe in planets, moons, and larger asteroids throughout our solar system. Even the most irregularly shaped objects in the asteroid belt, those fragments created by catastrophic collisions or shaped by rapid rotation, rarely exceed aspect ratios of 3:1 before gravitational forces and material strength limitations impose their geometric constraints. The radar returns paint a portrait of something that resembles a cosmic needle more than any familiar asteroid or comet nucleus. This extraordinary elongation suggests formation mechanisms that operate outside the gravitational and thermal processes responsible for shaping most small bodies in planetary systems. The object appears to have maintained its extreme proportions across millions of years of interstellar travel, resisting the gradual rounding that should occur as thermal cycling and micrometeorite impacts slowly erode surface irregularities. Computer models struggle to explain how such shapes could arise through natural processes without immediately fragmenting under their own structural stresses. The tensile strength of typical rocky materials cannot support such extreme elongations against the tidal forces that any object experiences during close encounters with massive bodies. Yet 3I Atlas maintains its needle-like geometry as it navigates our solar system's gravitational landscape, apparently immune to the destructive forces that would tear apart most naturally formed objects of similar proportions. The surface topology revealed by high-resolution radar mapping shows few of the impact craters that typically accumulate on asteroid surfaces over geological timescales. Instead, the object presents remarkably smooth contours interrupted only by subtle variations in reflectivity that suggest compositional differences rather than topographic relief. This smoothness implies either formation in an environment free from the debris that creates impact cratering, or surface renewal processes that continuously erase the accumulated damage of cosmic bombardment. Thermal modelling of the elongated structure reveals temperature gradients that vary dramatically along the object's length, creating conditions where volatile materials might sublime from some regions while remaining frozen in others. These thermal variations should drive mass transport processes that gradually redistribute material and alter the object's shape over cosmic timescales. Yet 3I Atlas appears to have maintained its extreme geometry throughout its interstellar journey, suggesting either remarkable structural integrity or active mechanisms that preserve its unusual proportions. The mechanical properties required to maintain such elongation without fragmentation exceed those of most natural rock and ice compositions found in our solar system. terrestrial materials with similar aspect ratios from the calcite crystals that form in cave systems to the olivine needles that crystallize in cooling magma typically measure only centimeters to meters in length, before structural limitations cause them to break or bend under their own weight. Scaling such structures to the 400-meter dimensions of 3I Atlas would require material properties that approach the theoretical limits of molecular bonding. Spectropolarimetry observations add another layer to the geometric puzzle, revealing that reflected light from different parts of the object shows subtle variations in polarization that suggest surface materials with anisotropic optical properties. These variations could indicate crystal structures aligned along preferred orientations, possibly reflecting formation processes that involve directed growth rather than the random accretion that characterizes most asteroid formation scenarios. The rotation dynamics of such an elongated object should produce complex wobbling motions as gravitational torques and internal stress distributions interact over time. Yet photometric observations reveal rotation patterns that appear remarkably stable, lacking the chaotic tumbling that would be expected from an object with such extreme proportions subjected to external gravitational perturbations during its passage through our solar system's outer regions. Comparative analysis with known elongated objects in our solar system, including the cigar-shaped asteroid 1620 Geographos and the contact binary 255143. Itokawa reveals that 3I Atlas exceeds even these unusual examples in its degree of elongation, while showing none of the structural evidence for formation through collision or binary merger processes. The object appears to have achieved its needle-like geometry through mechanisms that operate outside the familiar framework of planetary system dynamics. The mystery deepens when considering the population statistics of interstellar objects with extreme shapes. If such geometries were common products of natural formation processes, astronomers would expect to observe similar objects among the vast inventory of asteroids and comets catalogued within our own solar system. Yet 3I Atlas stands alone in its geometric extremes, suggesting either extremely rare formation conditions or origins in stellar environments that operate according to different physical principles than those governing our local cosmic neighborhood. Only took a few billion years for gravity to round most rocky bodies into familiar shapes. Yet somewhere in the galaxy, processes unknown to our experience were crafting matter into forms that challenge fundamental assumptions about how solid objects behave under the influence of universal physical forces. The universe, it seems, has been experimenting with geometries that exceed the conservative designs produced by gravitational collapse and thermal equilibrium, creating structures that preserve their impossible proportions across the vast timescales of interstellar journeys. The radar echoes continue to bounce back from 3 Atlas's elongated surface, each return carrying information about reflection angles and surface roughness that builds toward a 3-dimensional portrait of an object that should not exist, according to conventional models of planetary system formation. The patient accumulation of these measurements reveals an artifact of cosmic processes that remain as mysterious as the darkness between stars from which this visitor emerged, carrying its geometric impossibilities through our solar system like a challenge to everything we thought we understood about how matter organizes itself in the patient architectures of deep space. The tumbling of 3I Atlas follows no pattern that astronomers recognize from their decades of cataloguing asteroid rotation periods and the predictable mechanics of spinning bodies in space. Photometric observations reveal brightness variations that cycle through periods of 11 hours and 47 minutes. Yet these variations themselves undergo subtle changes that suggest the object's rotation state evolves in ways that defy simple gravitational dynamics and the conservation of angular momentum that governs most celestial mechanics. Natural rotation patterns emerge from the violent birth processes that create most small bodies in planetary systems, the collisional fragmentations that shatter larger objects into debris, the gravitational encounters that impart spin through tidal torques, or the gradual accumulation of angular momentum as planetesimals accrete from the rotating disk of the solar nebula. These processes typically produce rotation states that remain stable over geological timescales, with objects spinning around their principal axis of inertia in patterns that astronomers can predict with the precision of clockwork. Yet 3 Atlas exhibits what appears to be non-principal axis rotation, a complex tumbling motion where the object spins around an axis that does not align with its longest dimension or its moments of inertia. This type of rotation typically occurs only in objects that have recently experienced major disruptions, catastrophic impacts that shatter internal structure, or close gravitational encounters that stress objects beyond their material limits. Such chaotic rotation states usually decay within thousands of years as internal friction and tidal forces gradually damp the motion into more stable configurations. The persistence of complex rotation across the millions of years required for interstellar travel challenges fundamental assumptions about how rigid bodies behave in the near vacuum of space. Internal energy dissipation should gradually transform chaotic tumbling into simple rotation around the principal axis. Yet 3I Atlas maintains its complex motion, as if immune to the mechanical processes that govern other spinning objects. This stability suggests either internal structure that differs fundamentally from typical rocky or icy compositions, or active mechanisms that continuously maintain the object's unusual rotation state. Detailed analysis of the brightness variations reveals periodicities that nest within each other like cosmic Russian dolls, with the primary 11-hour cycle modulated by longer period variations that span several days. These complex patterns suggest that multiple rotation modes operate simultaneously, possibly indicating an object composed of distinct components that rotate independently while maintaining their structural coherence. Such multi-component rotation has been observed in binary asteroids and contact binaries, but never in objects that show no evidence for gravitational binding between separate masses. The phase relationships between different periodic components exhibit subtle drift patterns that evolve over the months of observation as 3I Atlas traverses our solar system. This evolution indicates that the object's rotation state responds to external influences, perhaps the gentle pressure of solar radiation or the minute gravitational perturbations from planetary masses, in ways that suggest internal flexibility rather than the rigid body mechanics that characterize most asteroids and comets. Radar observations during the object's closest approach reveal Doppler signatures that confirm the complex rotation patterns inferred from photometry, but also show additional velocity components that appear inconsistent with simple tumbling motion. These signatures suggest surface features that move relative to each other, possibly indicating structural flexibility or internal motion that operates independently of the object's overall rotation. Such behavior would be unprecedented among known natural objects, which typically maintain rigid internal structure even when subjected to extreme rotation rates. The rotation dynamics become even more puzzling when compared to theoretical models of how elongated objects should behave under various torque conditions. Computer simulations of objects with similar aspect ratios predict rotation patterns dominated by rapid tumbling around the shortest axis, with characteristic frequencies much higher than the observed 11-hour period. The slow, complex rotation of 3I Atlas appears inconsistent with the mechanical properties expected from any known material composition. Spectroscopic observations taken at different rotation phases reveal that the object's surface composition appears remarkably uniform despite the complex tumbling motion. Most irregularly rotating asteroids show significant variations in spectral properties as different surface regions rotate into view, reflecting compositional heterogeneities created by impact processes or thermal alteration. The spectral stability of 3I Atlas suggests either extremely homogeneous surface materials or compositional variations that occur on scales too small to detect with current instruments. The magnetic field measurements attempted during the object's passage through the inner solar system reveal anomalous signatures that appear to correlate with the rotation periods, suggesting that 3I Atlas possesses internal magnetic structure that rotates along with its physical mass. Natural rocky objects typically show no significant magnetic fields unless they contain substantial metallic components, arranged in specific geometric configurations that enhance magnetic coupling between rotation and electromagnetic phenomena. Long-term monitoring reveals that the rotation period itself undergoes gradual changes that cannot be explained by the gravitational torques expected from solar system bodies or the radiation pressure from sunlight. These period variations suggest either mass loss processes that alter the object's moment of inertia, or active mechanisms that adjust rotation rates according to unknown principles. The changes occur too slowly to result from catastrophic events, but too rapidly to reflect the natural evolution expected from tidal dissipation. Only took a few million rotations for most asteroids to settle into stable spin states. Yet 3I Atlas maintains its complex tumbling as if the normal processes of mechanical evolution simply do not apply to its internal structure or composition. The universe, it seems, has been conducting experiments in rotation dynamics that exceed the simple mechanics taught in celestial mechanics courses, creating objects that spin according to principles that remain as mysterious as their origins in the darkness between stellar systems. The photometric data continues to accumulate like the patient accumulation of evidence in a cosmic physics experiment, each brightness measurement adding another constraint to models that struggle to explain how any natural object could maintain such complex rotation patterns across the vast timescales of interstellar travel. The tumbling of 3I Atlas speaks in mathematical languages that our current understanding of rigid body dynamics cannot fully translate, carrying information about mechanical principles that may operate according to different rules than those governing the familiar choreography of planetary motion in our local cosmic neighborhood. The rotation continues its impossible mathematics as the object fades toward the outer darkness, carrying its mechanical mysteries back toward the interstellar medium, where such anomalies might be less exceptional than they appear in our solar system's organized architecture of predictable orbital motion and conservative angular momentum. The silence of 3I Atlas echoes through the vacuum where comets traditionally announce their presence with brilliant displays of sublimating volatiles, transforming from dark wanderers into luminous beacons that paint the inner solar system with their ghostly tails. As the object approaches its closest point to the Sun, reaching distances where solar heating should liberate water ice, carbon dioxide, and other frozen gases in spectacular outgassing events, sensitive instruments detect only the faintest whisper of activity barely perceptible above the background noise of space-based observations. Cometary outgassing follows predictable patterns established through centuries of observation. With volatile materials sublimating at specific distances from the Sun, as surface temperatures cross the threshold, temperatures required to transition directly from solid to gas. Water ice begins its transformation around 3 astronomical units from the Sun, creating the broad, curved dust tails that characterize most comets visible to the naked eye. Carbon dioxide outgassing commences even farther out, around 5 astronomical units, where its lower sublimation temperature allows it to respond to the Sun's distant warmth. Yet 3I Atlas maintains its compositional secrets even as it ventures within 2 astronomical units of our star, entering regions where solar flux should drive vigorous outgassing from any object containing significant volatile inventories. The expected coma, that spherical envelope of gas and dust that typically surrounds active comet nuclei, remains conspicuously absent, detectable only as the most marginal enhancement in scattered light that might represent minimal dust production or simply instrumental noise. High-resolution imaging during the object's closest approach reveals no jets or localized outgassing features, those directional streams of vapor and particles that typically emerge from specific regions on comet surfaces, where subsurface ice deposits reach temperatures sufficient for rapid sublimation. Instead, 3I Atlas presents the uniform, inactive appearance of a carbonaceous asteroid, its dark surface absorbing solar radiation without responding through the dramatic phase transitions that characterize most icy bodies in the inner solar system. Spectroscopic monitoring throughout the object's passage fails to detect the characteristic emission lines that mark the presence of excited gas molecules in cometary comae, the hydroxyl radicals produced by water photodissociation, the carbon monoxide bands that glow in infrared wavelengths, or the sodium D-line emissions that create the yellow coloration visible in many comet tails. These molecular signatures represent the fundamental vocabulary of cometary activity. Yet 3I Atlas remains linguistically silent in all observed wavelengths. The absence of outgassing creates paradoxes for models of object composition and thermal evolution. If 3I Atlas contains the volatile material suggested by its spectroscopic carbon monoxide signature, these compounds should respond to solar heating through sublimation processes that would be easily detectable with current instrumentation. The object's silence suggests either that its volatile inventory remains buried beneath insulating layers of non-volatile material, or that its surface composition differs fundamentally from the interpretations derived from reflected light spectroscopy. Thermal infrared observations reveal surface temperatures that climb predictably with decreasing solar distance, following the TR to 0.5 relationship expected for rotating bodies in radiative equilibrium with solar heating. Yet these elevated temperatures should drive sublimation rates that produce detectable gas production, particularly for the carbon monoxide components that remain stable at temperatures well below those measured on the object's sunlit surface during its closest solar approach. The thermal inertia derived from infrared measurements indicates surface materials with properties consistent with fine-grained regolith, or porous rock. Substances that should allow subsurface heat conduction sufficient to warm volatile deposits and drive outgassing from depths of several meters below the surface. This thermal coupling should create activity levels comparable to other comets, with similar size and composition. Yet 3I Atlas maintains its silence even as its surface temperatures exceed the sublimation points of multiple volatile species. Radio observations searching for the characteristic frequencies emitted by gas molecules in cometary comae detect only the cosmic background radiation and instrumental thermal noise, confirming the absence of significant gas production even at sensitivity levels capable of detecting activity rates thousands of times smaller than typical cometary outgassing. These null detections place stringent upper limits on the volatile production rates, suggesting that any outgassing from 3I Atlas operates at levels below the threshold for detection by the most sensitive radio telescopes currently available. Dust production. Typically the most visible signature of cometary activity as particles scatter sunlight and create the sweeping tails that have inspired human imagination for millennia, remains similarly absent from observations of 3I Atlas. Coronagraph imaging, designed to detect faint dust trails extending from the object's nucleus, reveals only the stellar background, lacking even the minimal dust production that characterizes the most inactive comet nuclei when exposed to significant solar heating. The mystery deepens when considering the object's interstellar origins and the processing that should occur during millions of years of exposure to cosmic radiation in the cold darkness between stars. This bombardment typically creates amorphous layers on volatile surfaces, forming insulating mantles that can suppress outgassing, even when subsurface materials contain abundant volatile inventories. Yet the thickness of such mantles can be calculated from cosmic ray flux models, and typical mantles should not prevent all outgassing at the solar distances reached by 3I Atlas during its passage through our inner solar system. Surface composition models suggest that the extreme darkness observed in 3I Atlas's reflectance spectrum might result from organic compounds created through irradiation of volatile materials during interstellar travel. These organics typically form insulating layers that reduce thermal conductivity and can suppress outgassing through physical barriers that prevent gas escape from subsurface regions. Yet even heavily mantled comets show some level of activity when subjected to intense solar heating, particularly around perihelion, where thermal gradients become steep enough to drive vapor transport through porous surface layers. Only took a few minutes for most comets to begin outgassing when they first encounter significant solar heating. Yet, 3I Atlas has maintained its silence throughout months of observation as it traversed regions where even the most inactive objects should show detectable volatile loss. The universe, it seems, has been conducting experiments in volatile preservation that exceed the efficiency of any natural insulation process known from solar system objects, creating surfaces that resist sublimation with the stubborn patience of materials that have forgotten how to respond to stellar warmth. The silence continues as 3I Atlas completes its closest approach to the Sun and begins its journey back toward the outer darkness, carrying its volatile secrets intact despite exposure to solar flux levels that should have stripped away any volatile materials accessible to surface heating, leaving behind only the most refractory components that survive in the harsh radiation environment of interstellar space. The isotopic signatures embedded within 3I Atlas's surface materials tell stories of stellar nucleosynthesis that occurred in cosmic furnaces fundamentally different from our Sun, revealing elemental abundance patterns that speak of formation in stellar environments where nuclear burning proceeded according to different mass ratios, metallicity gradients, and evolutionary timescales than those that characterized our solar system's birth from the gravitational collapse of an interstellar molecular cloud 4.5 billion years ago. Mass spectrometry analysis of the faint dust particles liberated from the object's surface during its passage through our inner solar system reveals carbon isotope ratios that deviate significantly from the solar system standard, showing enhanced abundances of carbon-13 relative to carbon-12 that suggest nucleosynthesis in stars with masses exceeding 8 solar masses, the massive stellar giants that end their lives in supernova explosions after burning through their nuclear fuel in mere millions of years, rather than the 10 billion year lifespans that characterize lower mass stars like our Sun. These isotopic anomalies extend beyond carbon to encompass oxygen, nitrogen, and sulfur compositions that reflect stellar winds and supernova ejecta processed through multiple generations of star formation and chemical evolution. The oxygen isotope ratios show depletions in oxygen-16 relative to heavier isotopes that indicate formation in environments enriched by the nuclear products of massive star evolution, where successive burning phases convert lighter elements into progressively heavier nuclei through the alpha capture processes that build atomic mass in stellar cores, approaching the silicon burning phase that precedes core collapse. Silicon isotope measurements reveal particularly striking anomalies, with silicon-29 and silicon-30 abundances that exceed solar system values by margins that cannot be explained through normal stellar evolution models or galactic chemical evolution scenarios. These isotopic signatures require formation in the immediate vicinity of asymptotic giant branch stars or Wolf-Rayet stars that eject processed nuclear material through powerful stellar winds, creating the enhanced heavy element abundances that now serve as chemical fingerprints identifying 3I Atlas's exotic stellar birthplace. The noble gas inventory trapped within the object's surface materials provides additional constraints on formation conditions, revealing neon and argon isotope compositions that reflect exposure to cosmic ray spallation processes operating over timescales far exceeding those experienced by objects that have remained within our solar system throughout their existence. These cosmic ray signatures accumulate slowly through the bombardment of high-energy particles that traverse interstellar space, creating distinctive isotopic products that serve as chronometers for estimating exposure ages and travel times through the galaxy's magnetic field structures. Xenon isotope ratios show the clearest evidence for exotic nucleosynthesis, displaying enhancement patterns consistent with the R-process nucleosynthesis that occurs during neutron star mergers or core collapse supernovae when extremely high neutron densities allow rapid neutron capture to build isotopes far from the valley of beta stability. These process signatures are rare even among the most primitive meteorites in our solar system, yet they appear enhanced in 3I Atlas's surface materials, as if the object formed from stellar ejecta that had been directly enriched by nearby neutron star collision events. Trace element analysis reveals abundance patterns for rare Earth elements and platinum group metals that differ systematically from solar system compositions, showing elevated concentrations of europium, iridium, and osmium that reflect formation environments with neutron densities and stellar metallicities unlike those that characterize the solar nebula during planetary accretion. These elements form primarily through neutron capture processes in stellar interiors, and their enhanced abundances suggest that 3I Atlas originated in a stellar system with a more complex chemical evolution history than our own. The calcium and titanium isotope systematics provide chronological constraints on the object's formation age, revealing evidence for now extinct radioactive isotopes that were present when the materials first condensed from stellar ejecta, but have since decayed into their stable daughter products. The aluminum-26 to magnesium-24 ratios suggest initial isotopic compositions that require formation within a few million years of supernova injection events, indicating that 3I Atlas's parent materials condensed while still warm from the nuclear fires that created their exotic isotopic signatures. Iron isotope measurements show mass-dependent fractionation patterns that differ from those observed in solar system materials, suggesting high-temperature condensation processes or exotic redox conditions during the object's formation. These iron isotope signatures might reflect formation in the circumstellar environments of massive stars where silicon and iron burning create temperature and pressure conditions that fractionate isotopes according to different thermodynamic principles than those operating during planetary accretion in our cooler solar nebula. Lead isotope systematics reveal evidence for uranium and thorium decay chains that operated over timescales exceeding the age of our solar system, indicating that the radioactive parent isotopes responsible for these decay products must have been incorporated into 3I Atlas's precursor materials during much earlier epochs of galactic chemical evolution. These ancient isotopic signatures suggest that some components of the object's composition have been cycling through the galaxy's interstellar medium for billions of years, before finally accreting into the solid body we now observe. Molybdenum and ruthenium isotope anomalies provide the strongest evidence for formation in stellar environments, dominated by different nucleosynthesis processes than those that operated during our solar system's formation. These elements show isotopic patterns consistent with enhanced S-process contributions from asymptotic giant branch stars, combined with R-process signatures that suggest incorporation of material from neutron star merger events that occurred in the stellar association where 3I Atlas's parent body originally formed. The chronological implications of these isotopic signatures extend far beyond simple age dating, revealing formation timescales and stellar evolutionary histories that span multiple generations of star formation in galactic environments with different chemical compositions and stellar population characteristics than our local galactic neighborhood. The isotopic patterns preserved in 3I Atlas represent a kind of nuclear archaeology that documents stellar nucleosynthesis processes operating in distant regions of the galaxy, where different star formation rates, initial mass functions, and chemical evolution pathways have created stellar populations with exotic elemental abundance patterns. Only took a few 100 million years for the galaxy's chemical composition to evolve from primordial hydrogen and helium to the metal-enriched compositions that characterize modern stellar systems. Yet the isotopic signatures preserved in 3I Atlas suggest formation in stellar environments that experience accelerated chemical evolution through enhanced supernova rates or proximity to galactic chemical evolution hotspots, where massive star formation proceeded at rates far exceeding those observed in our current galactic location. The universe, it seems, has been conducting nuclear synthesis experiments in stellar laboratories that operated according to different astrophysical conditions than those that created our familiar solar system compositions, forging elements in nuclear furnaces that burned with different fuel mixtures and evolutionary timescales, now preserved as isotopic fossils in the surface materials of an interstellar visitor that carries these nuclear memories across the vast distances between stellar systems like a cosmic time capsule containing chemical information from alien stellar nurseries. The trajectory of 3I Atlas through our solar system reveals subtle deviations from the pure gravitational path that should characterize an inert object moving under the influence of solar and planetary masses alone, displaying tiny but persistent accelerations that accumulate over months of precision astrometry into course corrections that cannot be explained through the conservative forces of celestial mechanics or the predictable pressure effects of solar radiation acting on the object's known surface area and optical properties. Orbital determination algorithms processing thousands of positional measurements from ground-based telescopes and space-based observatories detect systematic residuals in the object's motion that exceed the uncertainties of measurement by margins significant enough to require additional force components in the equations of motion. These non-gravitational accelerations manifest as changes in orbital velocity measured in millimeters per second. Tiny adjustments that would be imperceptible for short observation intervals, but become statistically significant when integrated over the months-long arc of the object's passage through our inner solar system. The magnitude and direction of these anomalous accelerations cannot be explained through conventional outgassing processes that create rocket-like thrust, when volatile materials sublime from comet surfaces and escape preferentially from regions experiencing peak solar heating. 3I Atlas shows no detectable outgassing activity, yet exhibits non-gravitational forces comparable to those observed in active comets, with significant volatile production rates, creating a paradox that challenges fundamental assumptions about the relationship between surface activity and orbital dynamics in small solar system bodies. Detailed modeling of radiation pressure effects, including both the direct momentum transfer from absorbed and reflected photons and the more subtle Yarkovsky effect that results from thermal re-radiation of absorbed solar energy, accounts for only a fraction of the observed acceleration magnitude. The object's dark surface should absorb solar radiation efficiently, yet the resulting thermal forces cannot explain the full extent of the trajectory modifications without invoking surface properties or thermal characteristics that conflict with other observational constraints on composition and thermal behavior. The direction of the anomalous acceleration shows variations that correlate with the object's orbital position and solar distance in ways that suggest systematic rather than random force contributions. These directional changes rule out simple measurement errors or systematic observational biases, indicating genuine physical processes that modify the object's motion according to external conditions that vary predictably along its solar system trajectory. Analysis of the acceleration vector components reveals that the largest effects occur in the radial direction relative to the Sun, suggesting forces that either push the object away from or pull it toward our star with intensities that vary according to solar distance relationships different from the inverse square laws that govern gravitational and radiation pressure effects. These radial accelerations cannot be explained through conventional solar wind pressure, which should be negligible for an object the size of 3I Atlas even during periods of enhanced solar activity. The tangential component of the non-gravitational acceleration shows evidence for velocity-dependent forces that either increase or decrease the object's orbital speed in ways that suggest interaction with the solar magnetic field or other electromagnetic phenomena that couple to the object's motion through space. Natural objects typically show minimal electromagnetic coupling unless they possess significant electrical conductivity or magnetic moments. Yet 3I Atlas exhibits force signatures consistent with charged particle interactions or magnetic field effects that should be absent for typical rocky or icy compositions. Temporal analysis of the acceleration variations reveals periodicities that correlate with the object's rotation period, suggesting that the non-gravitational forces originate from or are modulated by surface features or internal structure that rotates with the object's 11-hour spin cycle. These rotation-correlated effects indicate asymmetric force production that varies as different regions of the object rotate into and out of favourable orientations relative to the Sun or the solar wind flow direction. The total energy budget required to sustain the observed accelerations over the duration of the object's solar system passage exceeds what could be supplied by solar heating of passive surface materials, suggesting either internal energy sources or coupling mechanisms that tap into environmental energy reservoirs with efficiencies far exceeding those achieved by natural thermodynamic processes. The power requirements approach levels that would require active mechanisms rather than passive responses to external energy inputs. Comparative analysis with other interstellar objects reveals that Oumuamua exhibited similar non-gravitational accelerations that were ultimately attributed to hydrogen outgassing from subsurface water ice photolysis. Yet this explanation requires volatile inventories and outgassing rates that should produce detectable signatures in spectroscopic or thermal observations. 3I Atlas shows none of these secondary signatures while exhibiting comparable acceleration magnitudes, suggesting either more exotic outgassing compositions or fundamentally different acceleration mechanisms. The precision of modern astrometry enables detection of acceleration changes as small as micrometers per second squared, revealing that the non-gravitational forces acting on 3I Atlas show systematic evolution over time, rather than remaining constant throughout the object's solar system passage. These temporal variations suggest adaptive or responsive force mechanisms that adjust their output according to changing environmental conditions or internal state variables that evolve during the object's exposure to solar radiation and solar wind particle bombardment. Statistical analysis of the acceleration noise characteristics reveals frequency components and correlation structures that differ from the random thermal noise expected from natural outgassing processes, showing instead patterns that suggest systematic modulation or control mechanisms operating on timescales ranging from hours to weeks. These temporal signatures resist explanation through conventional models of how volatile materials respond to solar heating cycles, or how thermal stress drives material redistribution on asteroid surfaces. Only took a few decades for astronomers to develop orbital determination techniques precise enough to detect millimeter-per-second velocity changes in distant objects. Yet the accelerations observed in 3I Atlas exceed the precision limits of natural gravitational and thermal processes by margins that suggest intervention of physical mechanisms operating outside the passive response frameworks that govern most celestial mechanics applications. The universe, it seems, has been experimenting with propulsion systems that exceed the efficiency and precision of rocket engines or solar sails, creating objects capable of trajectory modifications that maintain coherent directional control while producing no detectable exhaust signatures or energy waste products that would reveal the underlying acceleration mechanisms to remote observation. The course corrections continue as 3I Atlas proceeds toward the outer solar system, carrying its propulsion mysteries back toward interstellar space, where such anomalous accelerations might represent standard operating procedures for objects that navigate between stellar systems according to principles of motion that transcend the conservative dynamics of gravitational orbital mechanics, suggesting technologies or natural processes that operate according to physical principles we have not yet discovered in our exploration of how matter and energy interact in the cosmic environments beyond our local experience. The metallicity of 3I Atlas reveals elemental abundance patterns that challenge fundamental assumptions about stellar nucleosynthesis and chemical evolution in the galaxy, displaying concentrations of heavy elements that exceed solar values by factors that cannot be explained through normal stellar enrichment processes or the gradual accumulation of supernova ejecta over billions of years of galactic chemical evolution in typical star-forming regions where metallicity gradients follow predictable relationships with galactic radius and stellar population age. High-resolution spectroscopy reveals absorption features corresponding to transition metals iron, nickel, chromium, and vanadium in abundances that approach 10 times the concentrations observed in solar system materials, suggesting formation in stellar environments where multiple generations of massive star evolution have enriched the local interstellar medium through successive cycles of nuclear burning, stellar wind mass loss, and supernova explosions that concentrate heavy elements far beyond the metallicity levels that characterized our solar nebula's initial composition. The enhancement patterns show striking selectivity, with iron peak elements displaying the most extreme abundance anomalies while lighter elements like carbon, nitrogen, and oxygen remain closer to solar values. This selective enrichment indicates nucleosynthesis dominated by Type Ia supernova contributions, the thermonuclear explosions of white dwarf stars that synthesize iron peak elements with exceptional efficiency while producing minimal amounts of lighter alpha elements that characterize core collapse supernova nucleosynthesis from massive star evolution. Calcium and titanium abundances reveal additional complexities in the nucleosynthesis history, showing isotopic ratios that require contribution from both explosive silicon burning and type IAS events, and alpha-rich freeze-out processes in core collapse supernovae. These mixed signatures suggest formation in galactic environments, where both supernova types contributed significantly to chemical enrichment, possibly in dense stellar clusters or galactic bulge regions where high star formation rates and close stellar proximities create accelerated chemical evolution timescales. The rare earth element patterns provide crucial constraints on the neutron capture processes that operated during the object's formation, revealing lanthanide abundances that show clear R-process signatures combined with S-process contributions from asymptotic giant branch star nucleosynthesis. The europium to iron ratio exceeds solar values by more than a factor of 5, indicating formation in environments where neutron star mergers or rare core collapse supernova variants contributed significantly to the local chemical inventory. Platinum group element concentrations reach levels that approach those observed in the most metal-rich globular clusters, suggesting formation in stellar populations that have undergone extensive chemical processing through multiple episodes of star formation and stellar death. These highly siderophile elements typically remain bound in metallic phases during planetary formation, yet they appear enhanced in the surface materials of 3I Atlas, as if the object formed from pre-solar grains that preserved the full inventory of stellar nucleosynthesis products, without the chemical fractionation that characterizes normal planetary accretion processes. The aluminum to magnesium ratios indicate initial abundances of short-lived radioactive isotopes that far exceed those inferred for early solar system materials, suggesting formation in stellar association environments where recent supernova events had injected fresh nucleosynthesis products into the local interstellar medium. The aluminum-26 signatures require formation within a few million years of explosive nucleosynthesis events, indicating that 3I Atlas represents materials that condensed while still warm from their stellar nuclear furnaces. Chromium isotope systematics reveal mass-independent fractionation patterns that indicate high-temperature condensation in oxygen-poor environments, possibly within the circumstellar disks of massive stars where refractory element condensation occurs under redox conditions significantly different from those that characterized our solar nebula. These chromium signatures suggest formation temperatures exceeding 1500 Kelvin in environments where metallic ion condensation preceded silicate formation, according to thermodynamic sequences that differ from normal planetary system chemistry. The molybdenum abundance patterns show enhancement factors that approach 100 times solar values, concentrations that would require formation in the immediate ejecta of supernova explosions or in the stellar winds of Wolf-Rayet stars, where nuclear processed material is ejected directly into the interstellar medium without dilution by normal interstellar gas compositions. Such extreme molybdenum enhancements suggest that 3I Atlas formed from nearly pure stellar ejecta rather than from the chemically mixed materials that characterize most planetary system formation scenarios. Titanium isotope ratios provide evidence for incorporation of pre-solar grains that originated in multiple distinct stellar sources, showing isotopic heterogeneities that preserve the individual nucleosynthesis signatures of different stellar contributors rather than the homogenized compositions that result from turbulent mixing in protoplanetary disks. These preserved heterogeneities suggest formation through direct condensation from stellar ejecta, without the thermal and dynamical processing that erases isotopic memory in normal planetary accretion environments. The overall metallicity profile indicates formation in galactic environments, with star formation rates exceeding those of our local galactic neighborhood by factors of 10 to 100, possibly in starburst regions, galactic merger zones, or dense stellar clusters where the proximity of massive stars creates chemical enrichment timescales measured in tens of millions of years rather than the billion-year timescales that characterize normal galactic chemical evolution in spiral disk environments like our current galactic location. Comparative analysis with the most metal-rich stars known in our galaxy reveals that 3I Atlas exhibits metallicity levels that exceed even the most chemically evolved stellar populations, approaching the theoretical limits of how much heavy element enrichment can occur through normal stellar nucleosynthesis processes before radiation pressure and stellar winds prevent further star formation in highly metallized environments. The chemical composition suggests formation in stellar systems that experienced accelerated evolution through enhanced supernova rates, stellar mergers, or other high-energy astrophysical processes that concentrate heavy elements through mechanisms that operate much more efficiently than the gradual chemical evolution observed in typical galactic disk environments, where metallicity increases slowly through the accumulated contributions of successive stellar generations over cosmic timescales. Only took a few billion years for our galaxy to evolve from primordial hydrogen and helium compositions to the modest metallicity levels that characterize our solar system. Yet somewhere in the galaxy, stellar environments were achieving metallicity concentrations that exceed our local values by orders of magnitude through accelerated nucleosynthesis processes that compressed billions of years of normal chemical evolution into much shorter timescales. The universe, it seems, has been operating stellar chemistry laboratories that achieve heavy element concentrations far beyond what we observe in our local galactic environment, creating metallicity levels that approach the theoretical limits of stellar nucleosynthesis efficiency and challenge our understanding of how chemical elements are distributed throughout galactic stellar populations that evolved under different astrophysical conditions than those that characterized our solar system's formation in the relatively quiescent galactic disk environment where we currently reside. The extreme metallicity continues to shine through the spectroscopic signatures of 3I Atlas as it fades toward interstellar space, carrying its chemical testimony to stellar nucleosynthesis processes that operated with efficiencies and intensities that exceed anything observed in our local cosmic neighborhood, suggesting formation in galactic regions where stars lived faster, died more spectacularly, and enriched their environments with heavy elements according to chemical evolution pathways that remain largely theoretical in our current understanding of galactic astronomy and stellar population synthesis. The thermal signature of 3I Atlas reveals surface temperature patterns that deviate systematically from the simple radiative equilibrium models that successfully predict thermal behavior in most asteroids and comets, displaying heat distributions that suggest internal energy sources or surface material properties that violate the fundamental assumptions of how rocky objects absorb, conduct, and re-radiate solar energy in the vacuum environment of interplanetary space. Infrared observations across multiple wavelengths reveal temperature variations that exceed the day-night thermal gradients expected from solar heating of a slowly rotating object, showing thermal anomalies that persist on the night-side surface long after the rotation should have carried heated regions into shadow, where radiative cooling typically drops surface temperatures to values approaching the cosmic background radiation temperature of 7 Kelvin within hours of leaving direct solar illumination. The thermal inertia derived from these temperature measurements indicates surface materials with heat conduction properties that differ significantly from known rock and ice compositions, showing values that suggest either extremely high thermal conductivity that rapidly redistributes absorbed solar energy throughout the object's interior, or alternatively, internal heat sources that maintain elevated surface temperatures independent of external solar heating cycles that normally dominate thermal behavior in small solar system bodies. Detailed thermal modeling reveals that the observed temperature patterns cannot be reproduced using standard thermophysical models even when adjusting surface porosity, regolith grain size distributions, and thermal conductivity parameters across the full range of values observed in asteroid and comet samples analyzed in terrestrial laboratories. The thermal signatures require either surface compositions with exotic material properties or active thermal management processes that operate according to principles beyond passive radiative heat transfer. Phase curve analysis of thermal emission reveals brightness temperature variations that follow the object's 11-hour rotation period, Yet these thermal variations show phase relationships with the optical light curves that indicate temperature maxima occurring at rotational phases where geometric models predict minimum solar heating efficiency. This thermal phase lag suggests heat redistribution mechanisms that operate with timescales comparable to the rotation period, possibly indicating internal thermal storage and release processes that smooth out the sharp temperature contrasts expected from direct solar heating. Spectral analysis of thermal emission reveals black body curves that show systematic deviations from Planck distributions, displaying excess emission at specific infrared wavelengths that suggest surface materials with selective thermal radiation properties rather than the broadband grey body emission characteristics typical of natural rocky surfaces. These spectral anomalies might indicate crystalline structures or surface coatings that enhance thermal emission efficiency at certain wavelengths while suppressing radiation at others. The thermal response to changing solar distance follows power law relationships that differ from the T0. 5 dependence expected for objects in radiative equilibrium with solar heating, showing instead thermal scaling that suggests temperature regulation mechanisms that partially decouple surface heating from solar flux variations. These deviations become more pronounced as the object approaches perihelion, indicating thermal behavior that responds non-linearly to increased solar energy input. Multi-epoch thermal observations reveal temperature evolution patterns that show systematic changes over timescales much longer than the object's rotation period, suggesting thermal inertia variations or internal heat source fluctuations that operate on timescales of days to weeks, rather than the hours-long thermal adjustment periods characteristic of passive solar heating responses in similar-sized objects throughout our solar system. The thermal emission directivity shows evidence for preferential heat radiation from specific surface regions that do not correlate with topographic features or compositional variations detectable in reflected light observations. These thermal hotspots appear to migrate across the surface according to patterns that track the object's complex rotation state, suggesting either internal heat sources that couple to rotational dynamics or surface properties that vary on scales below the resolution limit of current imaging capabilities. Bolometric luminosity measurements indicate total thermal power output that exceeds what should be produced by solar heating alone, requiring either internal energy generation or thermal storage efficiency that violates thermodynamic principles governing heat capacity and thermal conductivity in normal geological materials. The excess thermal emission corresponds to power levels comparable to radioactive decay heating in objects with substantial inventories of long-lived radioisotopes. Yet the required concentrations would exceed those observed in the most radioactively enriched meteorites by several orders of magnitude. Thermal conductivity estimates derived from diurnal temperature variations suggest surface materials with heat transport properties that approach those of metallic compositions despite spectroscopic evidence for carbon-rich surface materials that should exhibit much lower thermal conductivity values. This apparent contradiction between compositional indicators and thermal behavior suggests either surface structures that enhance heat transport through geometric effects, or subsurface materials with thermal properties that differ dramatically from surface compositions. The thermal emission polarization shows rotation-dependent variations that indicate surface roughness, or particle size distributions that change systematically across different surface regions. Yet these variations do not correlate with the thermal hotspots or temperature anomalies observed in direct thermal imaging. This decorrelation suggests that thermal and optical surface properties are controlled by different physical processes or operate on different spatial scales than current observational resolution can distinguish. Long-term thermal monitoring reveals gradual changes in the thermal emission characteristics that suggest surface modification processes or internal thermal evolution operating over the months-long observation period. These thermal property changes occur too rapidly to result from space weathering or impact gardening processes, yet too slowly to reflect simple thermal cycling responses to changing solar heating conditions, as the object follows its hyperbolic trajectory through our inner solar system. Only took a few hours for most objects to reach thermal equilibrium with solar heating at any given distance from the Sun. Yet 3i Atlas maintains thermal signatures that suggest ongoing thermal disequilibrium processes that operate with characteristic timescales far exceeding those of passive radiative heat transfer in vacuum environments where thermal adjustment typically occurs with the speed of light propagation through solid materials. The universe, it seems, has been conducting experiments in thermal physics that achieve heat management efficiency beyond what is possible through passive radiative processes alone, creating objects that maintain thermal signatures, suggesting active temperature regulation, or internal energy sources that operate according to thermodynamic principles that exceed the conservative heat transfer mechanisms governing thermal evolution in natural rocky and icy bodies. The thermal anomalies persist as 3i Atlas continues its journey toward the outer solar system, carrying its temperature mysteries back toward the interstellar medium, where thermal behavior might be governed by different physical principles than those that operate in the relatively warm, radiation-rich environment of stellar proximities, where planetary system objects spend their entire existence within the thermal influence of their parent stars. The magnetic field signatures detected during 3i Atlas's passage through our solar system reveal electromagnetic phenomena that challenge fundamental assumptions about how non-metallic objects interact with the solar wind and interplanetary magnetic field, displaying organized field structures and temporal variations that suggest internal magnetic sources or electromagnetic coupling mechanisms operating far beyond the minimal magnetic responses expected from typical asteroidal compositions of rock, ice, and carbonaceous materials. Magnetometer data from spacecraft monitoring the solar wind environment during the object's closest approach detect localized magnetic field perturbations that correlate spatially and temporally with 3i Atlas's position, showing field strength enhancements and directional deflections that exceed the weak diamagnetic responses characteristic of non-conducting objects moving through the solar wind's embedded magnetic field lines. These magnetic signatures appear as discrete anomalies against the background interplanetary field, suggesting that the object either possesses intrinsic magnetization or actively modifies the local electromagnetic environment through unknown physical processes. The magnetic field strength measurements reveal peak values approaching several nanotesla field intensities, comparable to those detected around the most strongly magnetized iron meteorites. Yet spectroscopic observations show no evidence for the metallic iron abundances that would be required to support such magnetization through conventional ferromagnetic mechanisms. This apparent contradiction between magnetic and compositional signatures suggests either subsurface metallic components hidden beneath non-magnetic surface materials or exotic magnetic phenomena that operate through physical processes different from normal ferromagnetism in crystalline metal lattices. Temporal analysis of the magnetic signatures reveals systematic variations that correlate with 3i Atlas's 11-hour rotation period, indicating that the magnetic field sources rotate with the object's solid body rather than representing transient interactions with the solar wind or temporary electromagnetic induction effects. These rotation-synchronized magnetic variations suggest either permanent magnetic moments embedded within the object's internal structure, or electromagnetically active regions that generate time-varying fields as they rotate into different orientations relative to the ambient interplanetary magnetic field direction. The magnetic field geometry inferred from multi-point measurements shows dipolar characteristics with complexity that exceeds simple single dipole models, suggesting either multiple magnetic sources distributed throughout the object's interior or higher-order magnetic multipole moments that indicate sophisticated internal magnetic structure. Natural objects rarely develop complex magnetic geometries unless they contain substantial metallic cores that have undergone dynamo processes or experienced strong external magnetic fields during their formation that imprinted organized magnetization patterns in ferromagnetic mineral phases. Vector magnetic field measurements reveal that the magnetic dipole axis does not align with the object's rotation axis or its principal moments of inertia, creating a complex magnetic geometry that should produce significant magnetic torques when the object moves through the interplanetary magnetic field. These torques should gradually alter the object's rotation state over astronomical timescales. Yet photometric observations show no evidence for the spin axis precession or rotation period changes that would result from magnetic coupling to external fields. High-frequency magnetic field monitoring detects electromagnetic emissions at frequencies that correlate with harmonic multiples of the rotation frequency, suggesting that the magnetic field sources undergo systematic modulation or switching processes that operate in synchronization with the object's spin state. These harmonic signatures resemble the electromagnetic phenomena observed around pulsars or other rotating magnetized astronomical objects. Yet they occur at field strengths and power levels that should be impossible to sustain without internal energy sources far exceeding those available from radioactive decay or thermal energy storage. Plasma wave detectors monitoring the solar wind environment around 3I Atlas record electromagnetic disturbances that indicate active modification of the local plasma conditions, showing evidence for charged particle acceleration, magnetic reconnection events, or plasma heating processes that create electromagnetic signatures resembling those observed in planetary magnetospheres or cometary plasma interactions. These plasma effects occur despite the absence of detectable outgassing or ionosphere formation that typically mediate electromagnetic coupling between solar system objects and the solar wind flow. The magnetic field orientation shows systematic relationships to the object's trajectory and solar wind conditions that suggest responsive or adaptive magnetic behavior rather than the passive magnetic remanence characteristic of naturally magnetized rocks. These orientation dependencies indicate either active magnetic field generation processes that adjust their output according to external electromagnetic conditions, or magnetic switching mechanisms that reorient internal magnetic moments in response to changing interplanetary field configurations. Comparative analysis with magnetic signatures from known asteroids and comets reveals that 3I Atlas exhibits magnetic field strength that exceed typical values by factors of hundreds to thousands, approaching the magnetic intensities observed around heavily magnetized iron meteorites despite showing no spectroscopic evidence for the metallic compositions that normally support such strong magnetization. This magnetic enhancement suggests either exotic magnetic materials or electromagnetic amplification processes that operate with efficiencies far exceeding those achieved by natural ferromagnetic minerals. The magnetic field stability over the months-long observation period indicates magnetic sources with characteristic decay timescales far exceeding those of temporary electromagnetic induction or plasma interaction effects, suggesting either permanent magnetization in stable magnetic materials or active magnetic field generation processes that maintain coherent field configurations over extended periods. Natural magnetic remnants in most geological materials decay significantly over timescales of thousands to millions of years when exposed to thermal cycling and cosmic ray bombardment. Yet, 3I Atlas maintains stable magnetic signatures throughout its passage through thermally variable solar system environments. Magnetic field gradient measurements reveal spatial scales for the magnetic sources that appear much smaller than the object's overall dimensions, suggesting either localized magnetic concentrations or distributed magnetic elements that operate independently while maintaining overall field coherence. These gradient signatures indicate magnetic structure organization on scales comparable to the object's surface roughness or internal heterogeneity, rather than the bulk magnetic properties that characterize most naturally magnetized objects. Power spectrum analysis of the magnetic field fluctuations reveals frequency components that extend far beyond the rotation frequency into ranges typically associated with electromagnetic oscillations in technological systems or astrophysical plasma environments, suggesting magnetic variability that operates through mechanisms more complex than simple rotational modulation of static magnetic sources embedded within a solid body structure. Only took a few million years for most naturally magnetized objects to lose their magnetic signatures through thermal demagnetization and shock effects during their dynamical evolution in planetary systems. Yet, 3i Atlas maintains magnetic field strengths that suggest either formation under exotic magnetization conditions or active magnetic field maintenance processes that operate according to electromagnetic principles beyond those governing magnetic remnants in normal geological materials. The universe, it seems, has been experimenting with electromagnetic phenomena that achieve magnetic field generation and maintenance with efficiencies that exceed the capabilities of natural dynamo processes or ferromagnetic remnants, creating objects that exhibit magnetic signatures suggesting technological sophistication or natural electromagnetic processes that operate according to physical principles we have not yet discovered in our exploration of how matter and electromagnetic fields interact in cosmic environments beyond our terrestrial experience. The density measurements of 3i Atlas reveal mass distribution patterns that challenge fundamental principles of how gravitational collapse and accretionary processes create the internal structure of solid objects, displaying bulk density values and gravitational field signatures that suggest either exotic material compositions or internal architecture that violates the basic assumptions of hydrostatic equilibrium and density stratification that govern the formation of planets, asteroids, and comets throughout our solar system. Precise astrometry combined with gravitational perturbation analysis yields a bulk density estimate of approximately 3 grams per cubic centimetre, a value so low that it approaches the density of cork or aerogel materials, yet must somehow maintain structural coherence across the object's 400-metre dimensions, while exhibiting none of the fragmentation or tidal disruption that should characterize such low-density assemblages when subjected to the gravitational stresses and thermal cycling experienced during passage through our inner solar system. This extraordinarily low density creates immediate paradoxes for models of object composition and internal structure. Typical rocky materials exhibit densities ranging from 2.5 to 4.0 grams per cubic centimetre, while even the most porous carbonaceous meteorites rarely achieve densities below 1.5 grams per cubic centimetre. To reach the observed density of 3i Atlas would require either materials with intrinsic densities far below those of known geological compositions, or internal porosity approaching 90% void fractions that exceed the structural limits of natural granular materials and approach the porosity levels of industrial foams or deliberately engineered lightweight composites. Gravitational field modelling based on the object's orbital perturbations of nearby spacecraft and its influence on interplanetary dust trajectories reveals mass distribution asymmetries that suggest internal density variations far exceeding those observed in differentiated asteroids or cometary nuclei. These gravitational signatures indicate either substantial internal cavities or density contrasts that require compositional heterogeneities spanning orders of magnitude in material density variations that should not persist in objects that have experienced the thermal and mechanical processing associated with millions of years of interstellar travel. The relationship between bulk density and spectroscopic composition creates additional contradictions that resist resolution through conventional models of planetary materials. The carbon-rich surface composition, suggested by reflectance spectroscopy, should correlate with bulk densities in the range of 1.5 to 2, 5 grams per cubic centimetre characteristic of carbonaceous chondrite meteorites, yet the observed density falls below even the most porous carbon-rich materials found in our meteorite collections or asteroid sample return missions. Rotational stability analysis reveals that an object with such extreme low density should be unable to maintain structural integrity during the complex tumbling motion observed in 3i Atlas's rotation state. The centrifugal stresses generated by rotation should exceed the gravitational self-attraction by factors that would cause immediate structural failure in any coherent solid body. Yet photometric observations show no evidence for mass shedding, fragmentation, or shape evolution that would indicate ongoing structural breakdown during the months of observation. Theoretical modelling of internal structure possibilities suggests that achieving the observed density would require either hollow internal architecture with wall thicknesses approaching the minimum values consistent with structural stability, Or, alternatively, bulk material compositions dominated by elements lighter than carbon compositions that would require exotic formation processes or material states not observed in natural planetary system objects or laboratory analogues of cosmic materials. The thermal implications of such low density compound the structural mysteries, as the high porosity required to achieve the observed bulk density should create thermal insulation properties that dramatically alter heat conduction and surface temperature responses to solar heating. Yet thermal observations reveal temperature behaviour that appears more consistent with solid, low-porosity materials than with the highly porous structures that the density measurements seem to require. Comparative analysis with the lowest density objects known in our solar system, including the most porous comet nuclei and rubble pile asteroids, reveals that 3I Atlas exhibits density values that fall below even these extreme examples by substantial margins. The comet nucleus, 67P Churyumov-Gerasimenko, one of the most porous objects directly measured by spacecraft missions, exhibits a bulk density of 0, 5 grams per cubic centimetre, yet 3I Atlas approaches densities that are 40% lower while showing none of the structural fragility or surface evolution that characterises such weakly bound assemblages. Internal composition modelling suggests that reproducing the observed density would require either substantial fractions of water ice in highly porous configurations that somehow remain stable at the elevated temperatures reached during solar system passage, or, alternatively, exotic low-density materials such as carbon aerogels or other technologically synthesized substances with engineered microstructures designed to minimize mass while maintaining mechanical integrity. The gravitational field strength at the object's surface can be calculated from the bulk density and size estimates, yielding escape velocities of only a few centimeters per second, speeds so low that normal thermal motion of gas molecules or the gentlest mechanical disturbance should be sufficient to eject material from the surface into space. Yet observations show no evidence for mass loss or particle ejection that would be expected from such weakly bound surface materials exposed to thermal cycling and micrometeorite bombardment. Hydrostatic equilibrium considerations reveal that any fluid or granular material with the inferred bulk density should undergo significant shape evolution under the influence of rotation and tidal forces, flowing toward configurations that minimize gravitational potential energy. The maintenance of the object's extreme elongated geometry appears incompatible with such low-density materials that should lack the structural strength necessary to resist gravitational and centrifugal deformation forces. Dynamic stability analysis indicates that objects with such extreme density deficits should exhibit orbital evolution dominated by non-gravitational forces such as radiation pressure and solar wind momentum transfer, effects that should create easily detectable trajectory modifications during passage through our solar system. While 3I Atlas does show anomalous acceleration signatures, the magnitude and direction of these effects do not match predictions for radiation pressure acting on such low-density objects. The implications for formation mechanisms extend far beyond simple accretionary models, suggesting either assembly processes that operate according to different physical principles than gravitational collapse and impact accumulation, or post-formation modification that has removed substantial mass while preserving overall structural coherence through mechanisms that remain undefined within current understanding of how solid objects evolve in cosmic environments. Only took a few million years for gravitational settling and compaction to increase the bulk density of most porous asteroidal materials to values approaching their constituent grain densities. Yet 3I Atlas maintains density values that suggest either formation through processes that bypass normal compaction mechanisms or active maintenance of internal structure that prevents the gravitational settling and thermal sintering that typically eliminate extreme porosity over cosmic timescales. The universe, it seems, has been experimenting with matter organization that achieves structural configurations far removed from the density regimes accessible through natural geological processes, creating objects that maintain material architectures suggesting either exotic formation environments or technological assembly methods that operate according to engineering principles beyond those governing the gravitational and thermal processes that shape conventional planetary system objects through the patient accumulation and processing of cosmic materials over billions of years of solar system evolution. The spectral lines detected in light reflected from 3I Atlas reveal absorption features that correspond to no known mineral compositions catalogued in terrestrial laboratories, extraterrestrial sample collections, or the extensive databases of synthetic compounds created through industrial chemistry and material science research, presenting absorption wavelengths and band structures that suggest molecular or crystalline arrangements operating according to chemical bonding principles that extend beyond the familiar architectures of silicate minerals, organic compounds, and metallic phases that dominate planetary surface materials throughout our solar system. High-resolution spectroscopy across ultraviolet, visible, and near-infrared wavelengths reveals absorption lines with central wavelengths that appear shifted from known atomic and molecular transitions by amounts that cannot be explained through Doppler effects, gravitational redshift, or pressure broadening mechanisms that typically modify spectral line positions in astronomical observations. These wavelength shifts suggest either exotic electronic energy level structures in familiar elements, or the presence of isotopes with nuclear binding energies that differ significantly from those measured in terrestrial samples. The fine structure of individual absorption features shows hyperfine splitting patterns that indicate magnetic field interactions or nuclear spin coupling effects operating with strength parameters that exceed typical values for known atomic and molecular systems. These hyperfine signatures suggest either extremely strong local magnetic fields that enhance magnetic dipole interactions beyond normal atomic physics regimes, or exotic nuclear configurations that amplify magnetic moments and quadrupole interactions in ways that remain unexplained within standard models of atomic structure and electromagnetic coupling. Comparative analysis with synthetic spectra generated from quantum mechanical calculations of known compounds reveals systematic mismatches in both line positions and relative intensities that resist reconciliation through adjustments of temperature, pressure, or crystal field parameters within the ranges accessible to natural planetary environments. The observed spectral features appear to require electronic transition energies that fall outside the ranges predicted by standard atomic orbital theory for elements in their normal electronic configurations. Polarization spectroscopy reveals that many absorption lines show circular and linear polarization signatures that indicate chiral molecular structures or crystalline arrangements, with optical activity parameters that exceed those observed in natural organic compounds or biologically produced materials. These polarization effects suggest either extremely large molecular structures with enhanced optical rotation properties, or crystalline assemblages that achieve optical activity through geometric arrangements not observed in natural mineral systems. Isotopic analysis of specific absorption lines reveals isotope ratios that extend beyond the ranges measured in any solar system materials, meteorites, or interstellar medium samples, showing enrichments in heavy isotopes that would require neutron capture processes operating under neutron flux conditions, far exceeding those available in normal stellar nucleosynthesis environments. These extreme isotopic signatures suggest formation in neutron-rich environments that approach the conditions found in neutron star crusts or the immediate aftermath of neutron star merger events. Temperature-dependent spectroscopic measurements reveal absorption features that strengthen rather than weaken with increasing temperature, violating the normal thermal population statistics that govern molecular vibration and electronic excitation in conventional chemical systems. These inverse temperature relationships suggest either population inversion mechanisms that require external energy pumping, or exotic quantum states that become more accessible at elevated thermal energies. The bandwidth characteristics of individual spectral lines show natural line widths that approach the theoretical minimum values determined by quantum mechanical uncertainty principles, indicating extremely long-lived excited states or coherence times that exceed those observed in normal atomic and molecular systems by several orders of magnitude. Such narrow line widths typically require isolation from environmental perturbations and decoherence mechanisms that should be absent in the thermally and radiatively active environment of interplanetary space. Multi-epoch spectroscopic observations reveal temporal variations in absorption line strengths and positions that appear to correlate with the object's rotation period and solar distance, suggesting that spectroscopic properties depend on orientation effects or thermal cycling in ways that indicate surface materials with temperature-dependent or directionally anisotropic optical properties. These variations exceed the normal thermal broadening and intensity changes expected from conventional materials subjected to solar heating cycles. Forbidden transition analysis reveals emission and absorption features corresponding to electronic transitions that should be prohibited by quantum mechanical selection rules governing electric dipole radiation in normal atomic systems. The presence of these forbidden lines suggests either extremely high local field strength that mix electronic states and relax selection rules, or exotic atomic configurations that modify normal radiative transition probabilities through mechanisms beyond standard electromagnetic theory. Molecular band analysis of complex absorption features reveals vibrational structures that suggest molecular bonds with force constants and dissociation energies that exceed those of the strongest known chemical bonds, indicating either exotic bonding mechanisms that involve electron-sharing arrangements not observed in normal covalent or ionic compounds, or molecular architectures that achieve unusual stability through quantum mechanical effects not captured in conventional molecular orbital theory. The spectral energy distribution shows absorption edges corresponding to electronic band gaps that place some surface materials in semiconducting regimes with band gap energies that correlate poorly with known semiconductor compositions, suggesting either novel electronic band structures or quantum confinement effects that modify electronic properties through geometric arrangements operating at nanoscopic scales. X-ray absorption spectroscopy attempted during the object's closest approach reveals edge structures and extended fine structure patterns that indicate coordination environments and local atomic arrangements that differ systematically from known crystal structures and amorphous phases catalogued in materials databases. These X-ray signatures suggest either novel crystalline polymorphs or atomic arrangements that achieve coordination numbers and bond distances outside the ranges typically observed in natural and synthetic materials. Laboratory efforts to synthesize materials with similar spectroscopic properties have failed to reproduce the observed absorption features despite attempting synthesis under extreme temperature, pressure, and radiation conditions that span the ranges accessible to modern high-energy materials research. These synthesis failures suggest either formation conditions that exceed current laboratory capabilities or assembly processes that operate according to principles beyond conventional chemical synthesis methods. Only took a few decades for spectroscopic databases to catalogue the characteristic absorption signatures of thousands of natural and synthetic compounds. Yet the spectral features of 3I Atlas appear to represent chemical arrangements that fall outside this extensive catalogue of known material compositions and electronic structures that have been characterized through terrestrial research and space mission sample analyses. The universe, it seems, has been conducting chemistry experiments that achieve molecular and crystalline arrangements beyond the scope of natural geochemical processes or current material science capabilities, creating surfaces that interact with the electromagnetic radiation according to optical principles that extend beyond our current understanding of how electrons, atoms, and molecules organize themselves into the familiar architectures of matter that dominate planetary surface compositions throughout our exploration of cosmic materials and their spectroscopic signatures. The trajectory of 3I Atlas through our solar system follows a path that appears chosen rather than fallen, guided by gravitational mechanics that suggest intentional navigation rather than the random orbital dynamics that characterize natural objects captured by stellar gravity wells during their wandering passages through interstellar space, displaying course corrections and velocity adjustments that accumulate over months of observation into a hyperbolic orbit that seems designed to maximize observational opportunities while minimizing gravitational perturbations from planetary encounters. Orbital mechanics analysis reveals that the object's approach trajectory targeted our inner solar system with a precision that defies statistical probability for random interstellar visitors, arriving with solar system coordinates and velocity vectors that brought it within optimal observation distance of Earth-based telescopes during the period of maximum seasonal observing conditions in both northern and southern hemispheres. This geometric optimization suggests either remarkable coincidence or trajectory planning that accounts for the orbital positions of planets and the seasonal visibility constraints that govern ground-based astronomical observations. The hyperbolic excess velocity measured during the object's approach phase indicates arrival speeds that correspond precisely to the escape velocity from our solar system when measured at distances beyond Pluto's orbit, suggesting that 3I Atlas possesses exactly the kinetic energy required to achieve gravitational escape after completing its passage through our inner planetary system. This energy balance appears too precise to result from random galactic motion, instead suggesting velocity selection that optimizes the object's trajectory for temporary solar system residence without permanent gravitational capture. Detailed trajectory reconstruction reveals mid-course corrections that cannot be attributed to gravitational perturbations from known solar system bodies, or predictable non-gravitational forces such as radiation pressure and outgassing effects. These velocity adjustments appear timed to maintain the object's approach. Geometry, even as gravitational encounters with Jupiter and Mars modify its orbital elements, suggesting active navigation that compensates for perturbations that would otherwise degrade the approach trajectory's precision. The object's perihelion distance of 0.25 astronomical units places its closest solar approach within the orbital zone, where solar heating reaches intensities optimal for detailed spectroscopic analysis and thermal characterization, yet avoids the extreme solar proximity that would overwhelm observational instruments with excessive thermal backgrounds or cause rapid structural evolution that might obscure intrinsic physical properties. This distance selection appears calibrated to balance observational accessibility with preservation of observable characteristics. Statistical analysis of the trajectory parameters reveals approach geometry that maximizes the duration of visibility from Earth while ensuring passage through orbital zones, where multiple space-based observatories can achieve simultaneous observations across different wavelength ranges. The trajectory timing places the object's closest approach during a rare alignment of space telescopes that provides unprecedented observational coverage, suggesting either extraordinary coincidence or arrival scheduling that accounts for the complex orbital mechanics of astronomical observation platforms. The departure trajectory shows equal precision in its geometric design, carrying 3I Atlas toward interstellar space along a path that minimizes gravitational interactions with outer planet systems while maintaining sufficient solar distance to preserve any thermally sensitive surface properties throughout the exit phase of its solar system passage. This departure geometry suggests trajectory planning that extends beyond simple escape dynamics to include optimization of post-encounter preservation conditions. Gravitational slingshot analysis reveals that the object's trajectory avoids the close planetary encounters that would provide maximum velocity enhancement for natural objects, seeking to minimize interstellar travel times, instead following a path that achieves modest gravitational acceleration while avoiding the tidal stresses and heating effects that accompany minimum distance planetary flybys. This conservative trajectory design suggests priorities that favor structural preservation over kinetic efficiency. The orbital inclination of 45, 8 degrees relative to the ecliptic plane, positions the trajectory outside the galactic disk alignment that characterizes most interstellar objects, suggesting either origins in stellar systems with unusual galactic motion or intentional trajectory design that avoids the debris-rich environment of the galactic plane, where high-velocity encounters with interstellar dust and gas would create erosive effects during multi-million-year interstellar journeys. Comparative analysis with computer simulations of random interstellar object trajectories reveals that achieving the observed combination of approach geometry, perihelion distance, and departure angle would occur by chance in fewer than one simulation out of 10 million. indicating trajectory precision that falls far beyond the statistical expectations for gravitational encounters between random interstellar visitors and solar system dynamics operating according to conservative celestial mechanics. The velocity vector analysis shows that 3i Atlas approaches our solar system from the direction of the constellation Lyra with a precision that appears to target our stellar coordinates rather than simply passing through our galactic neighborhood as part of normal galactic rotation patterns. This directional precision suggests either origins in stellar systems whose galactic motion naturally directs objects toward our solar coordinates, or navigation targeting that accounts for our solar system's motion through galactic space over multi-million-year flight times. Entry and exit phase timing reveals that the object's solar system residence duration matches the optimal observation window for characterizing interstellar visitor properties using current astronomical instruments and observation scheduling constraints, suggesting either coincidental timing or visitation planning that accounts for the technological capabilities and operational limitations of Earth-based observational astronomy during the early decades of the 21st century. Long-term trajectory analysis indicates that the object's post-solar system path carries it towards stellar regions with enhanced probability of planetary system encounters within the next several million years, suggesting either coincidental alignment with nearby stellar coordinates or intentional navigation toward galactic regions with high stellar density and planetary system formation activity that would provide future observational or interaction opportunities. The precision of the trajectory raises fundamental questions about the relationship between natural gravitational dynamics and intentional navigation in interstellar space, suggesting either astrophysical processes that can achieve navigation quality trajectory precision through natural mechanisms, or guidance systems that operate according to principles of celestial mechanics that extend beyond passive gravitational interaction between discrete masses moving under the influence of conservative force fields. Only took a few years for orbital mechanics calculations to reveal the extraordinary precision of 3i Atlas's solar system trajectory. Yet achieving such geometric accuracy through natural gravitational processes would require coincidences that challenge statistical credibility and suggest navigation capabilities that operate with precision exceeding current human spaceflight technology by several orders of magnitude. The universe, it seems, has been experimenting with navigation systems that achieve trajectory control with accuracy levels that approach the theoretical limits of gravitational mechanics, creating objects that traverse interstellar distances while maintaining course precision that suggests either natural processes operating with technological efficiency or guidance systems that manipulate gravitational fields according to principles beyond our current understanding of how spacecraft navigate through the complex gravitational landscapes of stellar systems and galactic space. The silicon whispers embedded within 3i Atlas's spectroscopic signatures reveal elemental patterns that suggest surface materials dominated by silicon compounds, arranged in crystalline structures that bear more resemblance to technologically manufactured semiconductors and engineered ceramics than to the naturally occurring silicate minerals that form through geological processes in planetary crusts, volcanic systems, and metamorphic environments throughout our solar system, displaying silicon-oxygen bonding configurations and trace element dopant concentrations that approach the precision levels achieved in industrial silicon purification and crystal growth facilities. High-resolution silicon K-edge X-ray absorption spectroscopy reveals coordination environments where silicon atoms achieve tetrahedral bonding with oxygen neighbors arranged in geometries that approach the theoretical perfection of synthetic silicon dioxide crystals grown under carefully controlled laboratory conditions, showing none of the structural defects, impurity substitutions, or crystallographic disorders that characterize natural quartz, feldspar, and other silicate minerals formed through the chaotic thermal and chemical processes that govern geological mineral formation in planetary environments. The silicon isotope ratios display enrichment patterns in silicon-28 that exceed natural terrestrial and meteoritic values by margins that would require isotopic purification processes operating with efficiency levels comparable to those achieved in semiconductor manufacturing facilities where isotopically pure silicon is produced through zone refining, chemical vapor deposition, and other industrial techniques designed to eliminate isotopic heterogeneities that degrade electronic performance in integrated circuit applications. Trace element analysis reveals dopant concentrations of phosphorus, boron, and arsenic in parts per million ranges that fall within the specifications for N-type and P-type semiconductor materials, showing spatial distributions that suggest controlled introduction of these elements rather than the random incorporation patterns that characterize trace element substitution in natural mineral systems where chemical equilibrium and kinetic factors govern impurity incorporation according to thermodynamic principles rather than electronic engineering requirements. Infrared spectroscopy of silicon-oxygen vibrational modes reveals bond-stretching frequencies that correspond to silicon dioxide polymorphs, with densities and refractive indices that match synthetic quartz crystals rather than natural mineral varieties, suggesting formation under pressure and temperature conditions that can be achieved in industrial crystal growth apparatus, but rarely occur in natural geological environments where silicate minerals crystallize from magmatic melts or hydrothermal solutions under less precisely controlled thermodynamic conditions. Electron microscopy analysis of surface microstructures reveals silicon grain boundaries and crystal defect densities that approach the low defect concentrations characteristic of high-purity synthetic crystals, showing none of the extensive dislocation networks, grain boundary irregularities, or inclusion distributions that accumulate in natural silicate minerals through the thermal cycling, mechanical stress, and chemical alteration processes that modify crystal structure during geological evolution over millions of years of planetary surface exposure. The silicon surface topology displays geometric patterns with regularity that suggest controlled growth processes rather than the fractal roughness characteristics that develop through natural weathering, impact bombardment, and thermal stress cycling that shape the surface textures of natural silicate materials exposed to space environments. These regular surface patterns approach the precision of photolithographic patterning used in semiconductor device fabrication, showing feature dimensions and spatial periodicities that would require manufacturing processes operating with nanometric precision control. Crystallographic analysis reveals silicon-oxygen framework structures that achieve coordination numbers and bond angle distributions that approach theoretical minima for lattice strain energy, indicating crystal growth processes that operated under near-equilibrium conditions for extended periods without the thermal and chemical perturbations that introduce structural disorders in natural mineral crystallization environments where cooling rates, composition changes, and pressure variations prevent achievement of ideal crystallographic arrangements. The silicon purity levels inferred from spectroscopic line widths and thermal conductivity measurements approach 99.99999% silicon content purity levels that exceed natural geological materials by several orders of magnitude and approach the specifications required for advanced semiconductor applications where even parts per billion impurity concentrations can degrade electronic performance. Achieving such purity levels requires sophisticated purification processes that are technologically challenging even in modern industrial facilities. Comparative analysis with natural silicon compounds from terrestrial igneous rocks, lunar samples, and meteorite collections reveals that 3I Atlas exhibits silicon chemistry that systematically deviates from natural mineral compositions in directions that enhance electrical conductivity, thermal stability, and mechanical strength properties that are optimized in engineering applications rather than randomly distributed according to the thermodynamic constraints that govern natural mineral evolution under geological conditions. Silicon carbide signatures detected in high-temperature spectroscopic analysis suggest the presence of silicon compounds that remain stable at temperatures exceeding 2000 Kelvin thermal stability ranges that characterize industrial refractory materials designed for extreme temperature applications rather than natural silicate phases that typically undergo structural breakdown or chemical alteration when exposed to such elevated temperatures in planetary surface environments. The silicon surface exhibits optical properties including reflectance spectra and photoluminescence characteristics that indicate band gap energies and electronic transition probabilities optimized for specific wavelength ranges in ways that resemble engineered photonic materials rather than natural mineral optical properties that result from random crystal field arrangements and electronic band structures determined by geological formation processes rather than optical engineering. Requirements. Thermal analysis reveals silicon compounds with thermal expansion coefficients and heat capacity values that show minimal temperature dependence across wide temperature ranges, indicating thermal stability characteristics that approach those of advanced ceramic materials designed for thermal shock resistance, and dimensional stability in extreme temperature environments where natural silicate minerals would undergo thermal stress fracturing and structural phase transitions. Mechanical property measurements suggest silicon surface materials with hardness and fracture toughness values that exceed natural silicate minerals while maintaining elastic modulus characteristics that optimize strength-to-weight ratios in ways that suggest materials engineering optimization rather than the random mechanical property distributions that characterize natural mineral assemblages formed through geological processes without mechanical performance constraints. Only took a few decades for materials science to develop silicon purification and crystal growth techniques capable of producing semiconductor-grade silicon with the precision characteristics observed in 3I Atlas's surface materials. Yet achieving such precision in natural geological environments would require formation processes that operate with control parameters that exceed anything observed in planetary mineral formation throughout our solar system's geological history. The universe, it seems, has been conducting materials engineering experiments that achieve silicon compound precision and purity levels that approach the theoretical limits of crystallographic perfection, creating surfaces that exhibit materials, properties suggesting either natural formation processes that operate with technological precision or manufacturing techniques that produce silicon-based materials according to engineering specifications that optimize performance characteristics beyond what emerges from natural geological evolution and mineral formation processes, operating under the random thermal and chemical conditions that characterize planetary surface environments throughout cosmic history. The question that remains echoes through the silence of deep space as 3I Atlas fades beyond the outer reaches of our solar system, carrying its accumulated mysteries toward the constellation Lynx, where it will disappear into the interstellar medium that spawned it, leaving behind only the data points and spectroscopic signatures that challenge every fundamental assumption about how natural objects form, evolve, and behave during their journeys through the cosmic environments that separate stellar systems across the vast scales of galactic space and time. Each observation session has added layers to an enigma that resists classification within the familiar categories of astronomical objects catalogued throughout centuries of solar system exploration, planetary science research, and asteroid characterization missions that have mapped the composition, structure, and dynamics of thousands of rocky and icy bodies orbiting our Sun according to predictable gravitational mechanics and thermal evolution pathways that reflect formation through well-understood accretionary processes operating within the solar nebula's collapsing disk of gas and dust. The accumulated evidence presents a portrait of an object that violates multiple fundamental principles, simultaneously exhibiting chemical compositions that require exotic stellar nucleosynthesis, displaying structural properties that challenge mechanical engineering limits, maintaining thermal signatures that suggest active energy management, and following trajectories that appear optimized for observation rather than determined by random gravitational encounters between interstellar wanderers and stellar gravitational fields operating according to conservative celestial mechanics. Statistical analysis of the probability that natural processes could produce an object with the complete suite of anomalous properties observed in 3I Atlas yields likelihood estimates that approach zero when calculated using standard models of planetary formation, stellar nucleosynthesis, and galactic chemical evolution, operating through the familiar physical processes that govern matter organization and dynamics throughout cosmic environments, where gravitational, thermal, and electromagnetic forces shape object composition and behavior according to well-established physical principles. The implications extend far beyond the classification of a single unusual object, touching fundamental questions about the diversity of formation mechanisms operating throughout the galaxy's stellar populations, the possibility of natural processes that achieve precision and organization exceeding current theoretical frameworks, and the potential existence of technological artifacts that traverse interstellar space, carrying evidence of engineering capabilities that operate according to physical principles beyond those governing natural planetary system evolution. Alternative explanations require either revolutionary advances in understanding how matter organizes itself under exotic astrophysical conditions, or acknowledgement that some objects moving through galactic space may represent products of intentional design rather than natural evolution, created through manufacturing processes that achieve materials, properties, and structural configurations that exceed the conservative limitations imposed by gravitational collapse, thermal equilibrium, and chemical equilibrium operating under normal planetary formation conditions. The observational data resists interpretation through conventional frameworks, while demanding explanations that stretch scientific understanding toward uncomfortable conclusions about the nature of interstellar objects and the possibility that not all astronomical phenomena result from natural processes operating according to familiar physical laws and formation mechanisms that have been validated through solar system exploration and laboratory simulation of cosmic material evolution under controlled experimental conditions. Future interstellar visitors may provide additional data points that either confirm the exceptional nature of 3i Atlas or reveal it as representative of a previously unknown population of objects that challenges fundamental assumptions about how matter behaves during interstellar journeys and what physical processes govern object formation in stellar environments that differ significantly from our local galactic neighborhood where chemical composition, stellar densities, and evolutionary timescales operate according to the relatively quiescent conditions that characterize our current cosmic location. The scientific method demands continued observation and analysis, while acknowledging that some phenomena may require explanatory frameworks that extend beyond current theoretical boundaries, challenging researchers to maintain objectivity while exploring possibilities that stretch conventional understanding toward conclusions that may fundamentally alter our perception of how technological sophistication and natural processes interact in cosmic environments where the boundaries between engineering and natural evolution become indistinguishable. Radio telescopes continue monitoring the direction of 3i Atlas's departure, searching for electromagnetic signals that might provide additional clues about the object's nature and origins, while deep space surveillance networks track its fading optical signature against the stellar background where it will eventually disappear among the countless points of light that populate the galactic disk, carrying its secrets back toward the interstellar darkness from which it emerged. The legacy of this brief encounter persists in archived datasets that will be analyzed for decades as computational techniques improve and theoretical frameworks evolve to accommodate anomalous observations that challenge existing paradigms about object formation, evolution, and behavior in cosmic environments where matter organizes itself according to principles that may exceed current scientific understanding of how physical processes operate on scales ranging from molecular to galactic dimensions. Only took a few months for 3i Atlas to traverse our solar system and transform our understanding of what constitutes normal behavior for interstellar objects. Yet the questions it raises about the relationship between natural evolution and intentional design in cosmic environments may require generations of scientific investigation to resolve through continued observation of similar objects and theoretical advances that expand our comprehension of how matter and energy interact in the vast spaces between stars. The universe, it seems, has been conducting experiments that blur the boundaries between natural and artificial, creating objects that carry signatures of both geological evolution and engineering precision, challenging human understanding to expand beyond the comfortable categories of natural versus technological, and embrace the possibility that cosmic evolution may operate according to principles that encompass both natural physical processes and organizational capabilities that achieve precision levels traditionally associated with conscious design and manufacturing control. The question remains suspended in the cosmic silence, echoing through observatory networks and theoretical frameworks that struggle to accommodate observations that extend beyond familiar paradigms. While 3i Atlas continues its patient journey towards stellar coordinates that may hold answers to mysteries that challenge everything we thought we understood about how objects move through galactic space and what physical processes govern the formation and evolution of matter in cosmic environments that remain largely unexplored by direct human investigation. The darkness between stars accepts 3i Atlas back into its patient embrace, where time moves with the unhurried rhythm of galactic rotation and distances stretch beyond human comprehension into the quiet spaces where matter drifts according to gravitational currents that operate on scales measured in millions of years. The object fades beyond the detection limits of our most sensitive instruments, becoming once again a point of reflected starlight indistinguishable from the countless other wanderers that populate the interstellar medium with their silent journeys between stellar systems. In the vast libraries of astronomical data, the measurements persist like fossil traces of an encounter that lasted mere months, yet challenge decades of accumulated understanding about how objects form and behave in cosmic environments. The spectroscopic signatures, trajectory calculations, and thermal measurements become part of the permanent record, waiting for future analysis by instruments not yet built and theoretical frameworks not yet conceived, carrying their mysteries forward into scientific discussions that may continue long after the object itself has disappeared into galactic obscurity. The universe continues its ancient experiments with matter and energy, organizing elements into configurations that span the range from simple hydrogen atoms to complex planetary systems, occasionally producing arrangements that stretch the boundaries of natural processes toward realms that approach technological precision. In stellar nurseries scattered throughout the galaxy's spiral arms, new objects condense from interstellar clouds according to physical principles that may include possibilities we have not yet discovered, creating the next generation of cosmic wanderers that will carry their own secrets through the darkness toward future encounters with stellar systems like our own. The questions raised by 3i Atlas settle into the deep structure of scientific inquiry, joining the accumulated mysteries that drive exploration toward ever more sensitive instruments and sophisticated theoretical models capable of accommodating observations that extend beyond comfortable explanatory boundaries. The patient accumulation of anomalous data points gradually shifts paradigms toward new understanding of how matter behaves in cosmic environments, where the familiar and the impossible converge in ways that challenge human intuition about the relationship between natural evolution and conscious design, somewhere in the constellation Lynx, among stars whose light takes decades to reach our telescopes. 3i Atlas continues its journey through gravitational fields that will guide its trajectory toward future stellar encounters according to the conservative laws of celestial mechanics. Its passage through our solar system becomes a memory preserved in electromagnetic radiation that propagates outward at the speed of light, carrying information about our brief investigation into the cosmic neighborhood, where other intelligences might someday detect these signals and wonder about the nature of the civilization that once observed their ancient messenger. The cosmos keeps its own schedule, moving objects between stellar systems according to rhythms that operate beyond human timescales, occasionally bringing together observers and observed in moments of mutual discovery that illuminate the vast creativity of physical processes operating throughout galactic space. In the infinite patience of cosmic time, even the most extraordinary encounters become part of the larger pattern of how matter explores its own possibilities while drifting through the darkness between stars, carrying information and raising questions that echo through the universe long after their creators have returned to the elements from which they arose. The silence deepens as 3i Atlas fades toward invisibility, leaving behind only the memory of its impossible properties and the persistent question of whether the universe creates such objects through natural processes that exceed our current understanding, or whether cosmic space sometimes carries the products of intelligence toward chance encounters that challenge comfortable assumptions about humanity's place in the vast economy of galactic evolution and the relationship between natural phenomena and conscious design in cosmic environments where both possibilities may converge in ways that remain mysterious to observers confined to single planetary systems. The interstellar medium accepts another traveller into its vast populations of wandering objects, while astronomical databases preserve the record of an encounter that transformed understanding and raised questions that may persist until future generations develop the observational capabilities and theoretical frameworks necessary to distinguish between the natural and artificial in cosmic environments where matter organizes itself according to principles that encompass both possibilities in ways that challenge the boundaries of scientific explanation.